So hello everybody, we are back to our plasma class. So today what we plan, we'll learn collisions in plasma. So collision plays a very important role in plasma in many aspects because the plasma equilibrium happens because of such collisions. Energy get transferred from one component to the other component. Electrons are the species which easily gain energy from the electric field. Then they collide with the neutrals, and depending on the collision frequency and the number density, it is decided whether equilibrium will reach or they will stay permanently in non-equilibrium. So before that, actually, let us go to the plasma equilibrium slide that we already discussed a little in the last class. That inside plasma, there are many things that is going on. As we already told that a plasma can be considered as a interpenetrating fluids of different kinds. Like if you are going for this multi-species model, then what you can assume that each species is different in its behavior. Or otherwise there is something called two fluid model where you basically consider electrons and ions and heavy particles. They are the fluids. So in one case, in two fluid model, you consider that electron species, they form one kind of fluid, and the heavy species, that includes the ions and the heavy particles, they form the other kind of fluid. Okay. So these two fluids are interpenetrated and energy is getting transferred from one species to the other. Now the electrons and the ions and heavy particles, it is not necessary that they will stay at a single temperature. So electrons may maintain their equilibrium at one temperature, say Te, the electron temperature, and the heavy species, they can maintain another equilibrium at a different temperature. So that temperature may be say Th. H corresponds to heavy and E corresponds to electron. Now the kind of distribution what they are observing, mostly you will see that they are obeying Maxwell-Boltzmann kind of distribution that I have shown on the right hand side. You see that this one, say delta NC is 4 pi n m by 2 pi kt to the power 3 by 2 e to the power mc square by 2 kt c square dc. That is the number of particles within speed range c and c plus dc. It is fine, but what we have put over here, this temperature is Te, and here this temperature is also Te. So this distribution is not necessarily the similar distribution for heavy species, where we have written the similar kind of distribution, but we are using a temperature Th. So this Th is basically heavy species temperature, and they need not be same as the electron temperature. So there are different kind of plasma formed depending on the pressure. For example, at lower pressure, what you get, you or electrons are getting enough mean path to gain energy from the field before they collide. So they can easily achieve a much higher temperature. Through collision, they are imparting their energy to the ions, but because of lower density, that exchange of energy from the electrons to the ions or heavy particles is not enough. So electrons are always maintaining a higher temperature, or they are staying at higher energy compared to the ions. For example, in the tube light that is in this class, we can touch the tube light by hand. You will feel that it is bit hot, but it will not burn your hand. But the electron temperature what is there, if you measure, it will be easily of the order of 1 to 2 electron volt. So the temperature 1 electron volt is 11,600, and you can understand what will be 2 electron volt. But when you are able to touch that you light by hand, the ion or gas temperature, that is definitely not that much, and it will be simply your temperature which your body can bear. So it may be say 35-40 degrees centigrade maximum. You are feeling little hot, that's all. So the difference in temperature between the gas particle, ions and the electrons, that is very huge in such systems. So they are non-equilibrium, but if you measure the distribution of the particles in the velocity or in the speed range, then you will find that they are more or less obeying Maxwell-Boltzmann kind of distribution. So electrons also doing the same and ions also doing the same, but they are maintaining the equilibrium at a temperature which are different. Electrons are maintaining their equilibrium at a temperature of Te, ions are maintaining their temperature at a temperature of Th. So that is the kind of thing as far as translational equilibrium is concerned. How this equilibrium is happening? Because of huge number of collisions that are undergoing simultaneously in the system, and that is basically resulting in the kind of distribution of velocities that we have just told. But there are other kinds of equilibrium also inside plasma. You know, plasma emits light. How? Because of the excitation of the atoms and molecules, rotational, vibrational levels. So when they de-excite, they emit the radiation, and that is the light what we are observing in a plasma discharge. So excitation of the atoms, ions and molecules is a very essential phenomena inside the plasma. Now, you know, the distribution of the electrons in different levels in atoms, that happens according to Boltzmann distribution. So that is given that this T excitation is the temperature corresponding to which this distribution is taking place. Now, when we are going to get this kind of distribution, the ith energy level having a population of this kind Ni, that equal to N0 Gi to the power Ei by kT. Ei is the energy of that ith level. And this Tx, we say it is the excitation temperature. How we can find it? You know that the ith energy level population will decide the intensity of the line that is getting emitted due to transition from that ith level. So if we note the intensity of the line that is getting emitted from the ith level, then that will be proportional to this one, this exponential factors. Of course, there is Gi. Now, this Gi and Ei, all these things are known for a particular system. For example, suppose you are handling argon plasma. Then for that, you know the energy levels. If you are getting a line radiation, you know from which level it is coming out, or for which transition it is corresponding. So if you know the line, the energy level, and under certain conditions you are getting the light emitted, the transition that is happening. So what is deciding the intensity of the transition? It is the Tex, excitation temperature. So if you heat it more intensely, you will get a more intense light, less intensely, less intense light. So this T is basically deciding the intensity. In other words, it is deciding the population of the ith energy level. Now, you see that intensity is now proportional to this exponential factor. Now, if you take log of that intensity, then it will be proportional to minus Ei by kT. Now, if you plot this log of this intensity as a function of Ei, then you can see that it is following an equation of the type y equal to mx plus c, isn't that? C will absorb rest of the constant terms, but essentially what you are getting y equal to mx. And what is the m? The slope of that line, that is 1 by kt. You understand that. Now what we are saying, intensity will be proportional to Ni, and if you write left side as Ni intensity, then I will be proportional to exponential of minus Ei by kt. If you take log of this intensity on the left hand side, then on the right hand side you will get this exponential will go and you will get minus Ei by ktx plus some constant. So if you plot this log of intensity as y and Ei as x, then what you are getting? Y equal to mx. What is m? It is 1 by kt and minus 1 by kt, so it will be just a falling line, and slope of that line will give you the 1 by kt value. So once you know the 1 by kt is the Boltzmann constant, you can find out the temperature Tex. So for any transition that is happening, it is rather easy to find out what temperature, at what temperature that emission is taking place. So that way you can know the excitation temperature of that system. For the same plasma system, there are various ways to find out what exactly the kind of distribution that it is following for the electrons as well for the heavy species. So you can know the electron temperature and heavy species temperature that is reigning over there. And the method that I just told you, using that you can understand what is the excitation temperature that is lying over there. Now the time comes for the ionization. Plasma is essentially a system which is having lots of ionized species, electrons and atoms. So if you are somehow able to find out the number of ions, number of neutrals and number of electrons that are present in a system at a particular discharge condition, then you can know the kind of relationship that it is following. You know the ionization energy here, and you know the partition functions of the specific system, and you are able to measure the number density of electrons, number density of ions and number density of neutrals. So just noting that, you can find out at what temperature this relationship is getting obtained. So from that you can find out the ionization equilibrium temperature. So when the system is in ionization equilibrium, they are maintaining a constant value of these ions, electrons and neutrals for that particular discharge condition. And for that particular discharge condition, you have already determined what kind of distribution the electrons are following, what kind of distribution the ions and heavy species are following, and what temperature the levels are populated. So you are already having the information of electron temperature Te, heavy species temperature Th, and excitation temperature Tex. Now just noting the relation that they are following for the ionization equilibrium that has been reached at that particular discharge condition, you can find the ionization temperature as well. So far what we have got, four kind of temperature here. One is electron temperature, one is heavy species temperature, one is excitation temperature, and one is ionization temperature, for which the ionization equilibrium is maintained. Now, you know, the radiation that comes out from sun is black body kind of radiation. So in a plasma system, it's large enough and they are having a very high temperature. Many of the times they radiate in a manner like a black body, but because of the dimension of the laboratory plasma is not high enough, so that absorption and emission, they do not equilibrate. So in small dimension plasma, we cannot have a radiation of the kind of black body. Rather, in systems like argon, monatomic systems, we get line radiations. However, there are Bemstrahlung because of the acceleration and deceleration of the electrons and ions inside the plasma, and for that we always do have a continuum as well. But the temperature at which the radiation is coming out of the plasma from the plasma, that may not be corresponding to the temperature corresponding to black body radiation. So you know that black body radiation formula, how it comes, the energy density of the spectrum, that gives you 8 pi h nu cube by c cube 1 by exponential h nu by kt rad minus 1. And in that actually the equilibrium, whatever the radiation intensity you are getting, you can get this equation plotted, and you can find out at what temperature the radiation equilibrium is maintained. And that whether this is T rad, this temperature T rad you can find out from by plotting this equation, and you can find that T rad is quite different from the other four temperatures what we have determined, like electron temperature, heavy species temperature, excitation temperature, and ionization temperature. And now we are landing upon the radiation temperature. You know this black body radiation. From the black body radiation we can determine the this temperature of sun, right? So for that actually what we use, actually lambda m t equal to constant formula. Lambda m is the wavelength at which you are getting the maximum temperature. Okay, so it is very easy to find out. You take a spectrometer, get the intensity recorded over a wide range of frequency, and you will see that almost at every frequency you are getting a radiation. That is the nature of black body radiation. It is a continuum radiation. So you will get a peak at certain wavelength in the intensity, and that wavelength where you are getting the maximum intensity is the lambda m. Lambda m is the wavelength corresponding to the maximum of the distribution. So once you know the lambda m, then lambda m into t is constant, and you know the value of the constant, then you can just find out the temperature from that, and that temperature will give you T rad. So it is very easy to find out T rad for a distribution of emission over the frequency range or wavelength range. You can find out T rad, and you do already have electron temperature, heavy species temperature, excitation temperature, and ionization temperature, your ionization equilibrium temperature. So all this equilibrium are getting maintained inside the plasma at different temperatures. Now, when we talk about the thermodynamic equilibrium inside the plasma, we are definitely talking about this temperature. We tell the plasma in complete thermodynamic equilibrium when this electron temperature, heavy species temperature, excitation temperature, ionization temperature, and radiation temperature all are the same. Then the system is in complete thermodynamic equilibrium. But local thermodynamic equilibrium, what is that? When, as I told you, in most of the laboratory plasma, they are not in radiation equilibrium because emission, your radiation get emitted from the plasma, but because of the limited size, very small size, small volume of the plasma, they don't get absorbed. They are just getting emitted. So it doesn't come into the equilibrium as far as radiation is concerned. So in such systems, in laboratory system mostly, we can achieve electron temperature, heavy species temperature, excitation temperature, ionization temperature, all same, but they are not same as the radiation temperature. So this is the one what we have we are talking about Te is equal to Th is equal to Tex is equal to T ion, but that is not equal to T radiation. So when such condition is achieved, then we say that it is local thermodynamic equilibrium. Now similarly, when similar things are maintained, but they're maintained in a special case. Actually, the CT and LT concepts, they are basically known to most of the students or most of the practitioners in the field. But as when this partial local thermodynamic equilibrium comes, then sometimes the this concept is not very clear. So let me clarify this part. When you are handling these arcs, for example, the degree of ionization that you achieve there, it is less than 0.1%. Okay. So 0.1% of the density that is of the order of 10 to the power 24 per meter cube in atmospheric pressure plasma, that is also quite large. So you are actually having a large density of electrons, but not large enough compared to the overall density. So it is only 0.01% of the species that is present there, they get ionized. So when this is the condition, the number of collisions with the neutrals are not sufficient to maintain the excitation temperature specifically the same as the electron temperature and heavy species temperature for many of the levels. To be specific, actually, suppose you have an atom. So the energy levels of the atom, as you come to the ground state, the first excited state, you have a very large gap. As you go to the second excited state, the gap reduces. If you go to the third excited state, the gap further reduces, and similarly goes on actually. So as you go upper and upper, the gap between two consecutive levels decreases, and a time comes when continuum starts. So if you have a collision, and what will be the energy transfer in that collision, it all depends, and the dependence is statistical. It may be very small, it may be very large, and there will be a group of collisions which have appreciable amount of energy. But if the number of collisions, number of events is less, then it is possible that in some moderate energy range you will get enough number of collisions, and you will always get a few collisions in very high energy range and very low energy range as well. So there will be a certain specific range of energy within which the energy exchange will take place, but they may not be very high enough or very low enough in other sectors actually. So for example, if we want to excite from ground state to first excited state, you will require a very high amount of energy because the gap is quite large. So it is not that you are not getting at all a collision which can excite from ground state to first excited state. But the thing is that when you are having such one or two collision, they will not make the states to reach their equilibrium population. When you are having very, very large number of collisions per second, then they will reach a equilibrium condition where they should be under the excitation equilibrium. Like that, suppose you are tossing a coin. So if you toss it, if it is only one event, you will either get head or you will get tail. But you know that the probability is 0.5, but if somebody does only once, he will see either tail or head. He will tell that why I am getting either tail or head, it is not 50% at all. But if you do very, very large number of such events of toss, then you will get half the time you will get the tail, half the time you will get head. They will be close to that, but they may not be exactly half and half. But if you really going to infinitely large number of such events, then you may get exactly 0.5 and 0.5. Similarly, when you are having a system where electron population is not appreciable, then what it happens that lower level populations are not as per the Boltzmann distribution because of the number of events are not good enough to maintain that equilibrium. But when you come to the higher energy states, they require very small energy or appreciably small energy for excitation from one level to another. So in that case, what you are getting? You are getting enough number of collisions. So there the equilibrium is maintained. So that is where you are getting equilibrium maintained for certain energy levels but not maintained, the excitation equilibrium is not maintained for lower lying energy levels. So depending on the kind of plasma that you have created, the pressure, the temperature, such things may happen. So this type of equilibrium is called partial local thermodynamic equilibrium. Is it possible to find out whether it is in LT or it is in PLT? Yes, it is very easy to find that out. As I told you that population of a certain energy level depends on the temperature that you have your plasma has achieved. Now at that temperature the excitation is happening, and because of the excitation you are getting some light emitted from that level. Now if you plot the intensity as a function of energy levels for number of such emissions which are occurring for different energy levels, then what you will find that because of the Boltzmann distribution nature, if you plot log of the intensity as a function of energy of the levels from which the emissions are taking place, then you should get a straight line. You will see in such plots in many of the laboratory plasmas like us, many of the energy levels are following a straight line for such kind of distribution where you are plotting the log of intensity as a function of energy levels, energy level values. So there you get a straight line and many of the emissions they are falling on the lines. But when you go for the emissions which are occurring from the lower lying states, you will see that they are not falling on a straight line. They are deviating quite a lot from that straight line. So this part we will discuss at length in our plasma diagnostic section, where we will go for the emission spectroscopic diagnosis, and I will show you real life examples of such things happening over there. So now you are clear about the concepts of CT, the complete thermodynamic equilibrium, LT, the local thermodynamic equilibrium, and PLT, the partial local thermodynamic equilibrium. CT and LT concepts are more or less clear and there are less ambiguity, but as far as PLT is concerned, there are some ambiguities. So that's why what I have done in this class, I have explained in very detail the PLT concept and why PLT happens and whether you can detect PLT for a plasma system very easily through some experiments. So this much now, and we'll meet in the next class. Okay, thank you.